Welcome everyone. Today we're talking about Reuben Louis Goodstein. Okay, he is a British mathematician, logician. He was a professor at the University of Leicester, and he worked in recursive arithmetic and ordinal numbers. The reason we're discussing him today is about the unusual theorem in 1944. So this is the Goodstein theorem from 1944. Here it's phrased as a question. I'll show you the theorem in the next step. Essentially, what it says is that start with a number, whatever number you have, and write it in the hereditary base B notation. That means, let's suppose you start with the base is 2. So write that number in the base 2 notation. That means write that number using any numbers up to and including 2, which only means 1 and 2. Then with each step, you bump the base. That means wherever you see a 2, you replace that with a 3. So you replace the base B with B plus 1. And finally, you subtract 1 and keep doing this thing. And the numbers become very large very quickly, by the way. The question is, where does the sequence terminate? Does it ever terminate? Does it hit infinity, etc.? So let's start with the number 4. So we'll write 4 as base B notation, base 2. So we'll write as 4 is equal to 2 power 2. Great. Now we simply bump the base. Wherever we see a 2, we replace it with 3, and then we subtract 1. So 2 power 2 becomes 3 power 3 minus 1, which is 26. But now we'll write 26 in the base 3 notation, but we won't use that subtraction symbol. That's not the notation. So what we'll say, 26 is 2 times 3 square plus 2 times 3 plus 2. Now again, we'll bump the base. So wherever we see a 3 here, we'll change that to a 4. So we have 2 times 4 squared plus 2 times 4 plus 2, and then subtraction 1, subtract 1. So that becomes plus 1. So now we have gone from 4 to 26 to 41. We do it one more time to 5. We get 60 again till 7. We get 83, 7, 109. And the numbers keep getting larger and larger. Let's go a little further. It's fun to play with these numbers. So now we are at base 5. So 2, 5 squared plus 2 times 5, 60. Now again, we bump the base. So wherever we see a 5, we make it a 6. So that means we have 2 times 6 squared plus 2 times 6 minus 1, which can then be written as 6 plus 5, right? Because we don't use the subtraction symbol. So now we're at 83. We go to 7. We get 109. And if we skip a few steps, we'll get to 212 squared plus 11, which is 144 plus times 2, 288 plus 11, 299. Okay. And we will eventually get 1058, 1151, etc., etc. So we can keep going, and we're at 40895. The question is, where does it terminate? And here's the theorem. The Goodstein Theorem from 1944 says that if you keep doing this operation that we've just discussed, the numbers become very large, but every Goodstein sequence will eventually reach 0. Now, this is not a philosophical answer. This is not a metaphysical answer, trick answer. In this case, we mean 0, the familiar 0, the number before 1. So the question is, does it actually go down? Yes, it does go down, but you have to look at it carefully to say, how does it actually go down? So think about it in terms of the terms of the polynomial. For example, we have at a certain point, base is 3, we have 3 squared plus 2 times 3 plus 2. This was from one of our terms. So we can write these polynomial terms as 2, 2, 2, which are these coefficients. The last one is constant term. This is x, this is x squared. Then we will change the base to y. So at a certain point, base y is 25, but the terms now look like 123, 22. So as per our familiar polynomial terms, we would say that 123, 22 is smaller than 222. 123, 22, after a few steps, 22 steps to be precise, it'll become 123, 0. Then it'll become 122, 47 again, and this term is less than this term. polynomially speaking, and I'm putting this polynomials in quotes. Then you'll get to 121, 0, 120, 191, 0, 0, 6. It has, even though that might be a large number. And then the slow decline begins. The slow decline as in only the subtraction 1, because there will be no base left to bump. And that's really the essence of this theorem. Even though the formal proof follows a slightly different outline, this is just how to build our own intuition. So if you want to see here, let's go back to step 4 here. So we were at 2 times 3 square plus 2 times 3 plus 2. When we go here, we get 2 times 4 square plus 2 times 4 plus 1. Finally, when we go till 6, we have 2 times 6 square plus 6 plus 5. So wherever we had 2 times 3, now it's only left with 1 6. Because this is now already a 5. This won't be bumped. When this 6 becomes a 7, this 5 will remain a 5. And when we do a subtraction, we'll get a 4. So that's why we get 2 times 8 squared plus 8 plus 3, 9 squared plus 9 plus 2, 10 plus 1, 11. And then at next step, we become 2 times 12 squared plus 11. Because we did bump this 11 to 12, we subtract 1. Now we're left with 11. Now this is not going to bump anymore. This will keep bumping. And eventually, this 2 times 24 square will become 2 times 24 square minus 1. And then we make it 24 squared plus 23 times 24. So we really lost this 2 here. So the numbers are getting larger, but if you think about it in terms of polynomial terms of these coefficients, they are actually becoming smaller. And that really is the Goodstein theorem, that it does become 0. Okay. So it does actually go down. And again, this is not a theoretical result or a trick result here. And if you start with 5, it's even more fun. Again, it's fun to play with it. You can say 5 is equal to 2 squared, 2 plus 1. It's only plus 1 different from the previous one, but the numbers become much larger even because of that 1. So we have 3 square, 3 power 3, then become 4 power 4. You can already see why it became larger here. And eventually, after a few steps here, you can follow this, do this math your own way if you like. We're looking at 45 million number here. So there is no real intuition. If you just look at the numbers, there's no real reason to believe that these numbers are going to go down, much less to 0. But they do eventually stop growing, and then they begin their decline by 1 to down to 0. So if you think about an analogy, it's almost like you have a bucket of water. In every step, you're doubling the amount of water in terms of making the bucket radius twice as much, but you take 1 drop away. And eventually, that leaky bucket comes down to empty. And it's very, side analogy here. So see if that helps you. Okay. So why does it terminate? What's the outline of the formal proof? The formal proof is that, and this was the nature of Goodstein's work, that he was working about ordinals. So he wrote about ordinals rather than thinking about infinity, which we would normally say the integers 1, 2, 3, 4, 5, 6, eventually they will become infinity. But he said, okay, rather than thinking in terms of infinity, let's try to put a numbering on it. So he called that ordinal to be omega, which is larger than any finite number. And then he said, okay, well, you can also have omega plus 1. You can have 2 omega, which is larger than omega, even though we normally call all those numbers that are infinity. And you can also have omega square, things like that. So that's how he imposed the ordering. And then he mentions that in the proof, if you bump the base, omega becomes omega plus 1, which is omega. So subtracting 1 will make the ordinal strictly smaller, and eventually you have to get down to 0. And therefore, every Goodstein sequence terminates at 0, starting with any number. Now, this is such an interesting result. So if you indulge me for a moment, this is how Goodstein's life turned out to be. real fun that he publishes this great theorem. Universities start establishing new research programs. This Goodstein principle becomes known everywhere. He is knighted. He looks at, he enters the Royal Society, and there's an institute in his name, etc., etc. A bunch of things could have happened. However, none of this happened. None of this happened. So this all is just you indulging me. So he publishes this great theorem in 1944, very elegant proof, but very little attention. This is just viewed as an interesting application of ordinal arithmetic, arithmetic of ordinal numbers. And it sat very quietly in the literature for 40 years. No attention, really. Then came the 1982 result by Kirby and Paris, which showed that Goodstein theorem is not provable in Peano Arithmetic. Peano Arithmetic, the one named after Giuseppe Peano. So it's one of the first natural independence results, and this has nothing to do with the Gödel sentence. It's not self-referential, as you just saw the theorem. There's nothing self-referential in it. It's just an ordinary theorem. It's just a theorem about, not ordinary, just a theorem about integers. It's a beautiful theorem about integers, but it's a theorem. It's not self-referential. And yet it has the same exact impact as that of the Gödel's incompleteness theorem. Quite similar. And that is really when the attention came. Now, if you notice, this is 1982. Goodstein passes away in 1985. So this is merely 3 years prior to his passing, that this work brought attention back to his work, to Goodstein's work. And these are the strange dynamics of discovery. That the theorem is beautiful, but sometimes, even though it's a beautiful theorem, it did not become famous. It became famous once it connected arithmetic, the concept of transfinite induction, which is what's used to show that this is not provable in PA, in Peano Arithmetic, and connected to Gödel's incompleteness, even though it has nothing to do with self-referential. And sometimes the history will reward this particular bridge more than the construction itself. And that's, I think, is a bit of a broader lesson here. Another lesson, I mean, sometimes some discoveries can wait decades before somebody understands what is the real significance of their work. As you notice, between 1944 and 1982, almost 40 years elapsed. But now it's considered a cornerstone example in proof theory. And sometimes, the importance of research is just going to be revealed by future generations. Okay, that's all I have for you today. Have fun, keep learning. Okay.